This is lecture 9G for Calculus 2 on draining fluids from cylindrical tanks. Now we're going to find the differential equation that governs the height of the fluid that's in the tank. And to do that, we start looking at the particular tank we have, and what we're going to look at here is a cylindrical tank. And what we were computing before was a rate of change of volume, so now we're going to look at volume in terms of this particular tank. Later on we'll look at volume in terms of a conical tank. So we start here. What is the volume in the cylindrical tank of radius RT, or the subscript T meaning for the tank? It's pi r squared times h. Let me draw the tank for you. I'm sure you know what a circular tank looks like. Probably doesn't look too much like this. Okay, so here is the radius of the tank, and h is the height of the fluid inside the tank. I'm letting 0 be at the ground. This really is a y-axis, and here's your h up here. This is the h is the level of the fluid inside the tank. Now that's a pitiful looking tank if I ever saw one. All right, so here is the volume of the fluid that's left in the tank. Say the fluid is draining from the tank, then the height of the fluid will change with time. All right, I'm going to take the derivative. If I take the derivative of this side, here, I get the rate of change of volume. When I take the derivative over here, I get pi r squared dh by dt. Pi doesn't change with time. The radius doesn't change with time. The only thing that changes with time is this fluid, which drains out of which decreases as the volume leaves the tank. All right, now I have one expression for dV by dt. I had another one from Torricelli's law. So let me write those over here. You can see what I'm doing. The rate of change of volume in a cylindrical tank is pi radius of the tank squared times dH by dt. From Torricelli's law, assuming a circular outlet pipe located somewhere down at the bottom of this tank, which we aren't even going to, I'm not going to touch that tank anymore, ended up being, okay, because it's draining, be minus 60 pi radius of the outlet pipe squared square root of 2g times the square root of h. Okay, both of these are dV by dt, so I equate them. Here is the result of Torricelli's law, and this has to do with the rate of change of volume inside of the tank, the particular tank that we've chosen. Right. So now you see we do have a differential equation in h. The rate of change of the height, and here we have the square root of h. Then we have a whole bunch of other constants, and I'll show you how to take care of them in the next slide. First thing I do is rearrange it so I get all the constants together. So here are all those constants right here. And this is the first derivative of the height of the fluid inside the tank, and here's the square root of the height. Everything else inside of here, inside of this yellow box, is a constant. Well, I don't like dragging all those constants around, and I can make a lot of errors if I do that, so I just abbreviate them, and in this case I abbreviated them as alpha. So then the equation just becomes dH by dt equals minus alpha times the square root of h. I left the minus sign in. Signs are important. Sorry about that. I shouldn't have made that all yellow. But I just abbreviated this as alpha. That's a lot better than trying to carry around 60 r squared times square root of 2g divided by the radius of the tank squared. Now I have something that looks fairly simple. I want to solve this. So here again is our differential equation, and it's separable. Okay. Remember the form for a separable equation? I'll write it out. Okay. You would have some function, I'm going to use y as the independent variable, dy by, say, dx equals n sub x. So everything on this side depends only on y, or it could be a constant. Everything over here depends only on x, or it can be a constant. So what we have here when we separate this out is we'll put all the h's over on this side. So I have h to the minus 1/2 times dH by dt, and the negative alpha can stay over here. I can rearrange and then I can integrate. So I have h to the 1/2, minus 1/2 rather, dh, and now I have an integral of minus alpha dt. Alpha is a constant, so this just becomes minus alpha t, and it's customary to lump all the constants of integration over on the right-hand side in 1c. Over here, of course, you would have h to the 1/2 divided by 1/2, so that gives you 2 square root of h for this side, and then the c is actually combined over on the other side. So that's what we get right here. Okay. Now you have this constant of integration which we can evaluate. So I'm going to erase everything on the screen, and then we're going to evaluate it. Say we know the initial height of the fluid before we start trying to drain it. So initial means t equals 0. Remember that. So h at time 0 is any old height. We want to call it h naught. Right. So substituting that into the equation, we can find a value for c. So we have 2 h naught to the 1/2 equals minus alpha times 0, so that's 0 plus c. C is equal to 2 times the square root, however you want to write it, of the initial height in the tank. Now, at this point, we had a general solution. Now that we've evaluated the constant, we can write it like this. Put the 2 on the other side. So we have h to the 1/2 equals minus alpha over 2 times t, and here we have plus 2 times the square root of h naught. Right? Now I can square both sides, and I get the square root. I could go 2 times h naught to the 1/2 minus alpha. Oops, forgot the 2 here. There was a 2 over here too, canceled out. Times t. There's my solution, and I'll show it to you again on the other side. But once I've evaluated the c, the point I want to make is now I have a particular solution. This particular solution, because I've evaluated c, general solution, here because I have not yet evaluated c. So here's the solution that I kind of wrote on the other page, but now you can see it more clearly. This is the height of the fluid in the tank equals this quantity, the initial height raised to the 1/2 power minus alpha over 2 times t, quantity squared, where alpha is all these constants left over from the initial setup of the problem. Now here's an example of how to use that solution. Say you had a cylindrical liquid feeding tank for your livestock, and it's 68 inches in diameter and 41 inches high. All right. Then, for some reason, a 2-inch diameter hole gets punched near the bottom of the tank. And the question is, how long does it take for all the fluid to drain out of the tank? Turns out it's not very long. Okay, so let's go back for a minute and get our original solution. Well, I can remember it, so I can write it down here for you. The height equals the initial height taken to the 1/2 power minus the alpha over 2 times t, quantity squared. This is how the height changes with time. I wonder if I have a white. I do. Okay. So this is the height in the fluid as it changes with time. These units were in inches, and you have to convert them to something. I convert everything to meters. Here's the radius of the tank, here's the initial height, and here's the radius of the outlet pipe. Well, it's not a pipe, it's a hole. Okay, we're on Earth, so here's the acceleration due to gravity in MKS units. I have to go back and find out and evaluate alpha. That was kind of complicated, but it's only a multiplication problem. Okay, here was our solution again. Here was alpha. If we take all those numbers we had on the other page and plug them in, we find that alpha is 0.23. So here is the height of the water in the feeding tank. I substituted for H naught 1.0414. the square root of that, minus, here's the alpha, 0.23 divided by 2t. Of course, I can divide that out. Here's my solution. This is how the height varies with time, and I'll show you a graph of it in a minute. All right? Now, if you want to find out how long it takes for the tank to get empty, set the height equal to 0. At that point, the tank is empty. And solve for t. It turns out it takes 8 minutes and about 9 minutes to drain that tank. So you can say that gravity works pretty well. I have read, but I have no experience with this, that some fire sprinkler systems are set up with tanks located on the roofs of buildings, and that the fluid drains out of them just under gravity, just as we have described it here. So if the electrical system fails, you still get water from these tanks. I have no experience with that. Maybe somebody knows something about that. So if you know anything about that, why don't you send me an email and let me know. Let me know if that's really true. Sometimes you read things and they have nothing to do with reality. So I like to get some information from someone who knows something about that. Okay, so here was our feed tank that we put out, our stock tank, and it got drained. So it started here. This was the initial height of the fluid. As you can see, it's not a straight line. It doesn't look too far from a straight line, but this is how it decreases. And this, at this point, it truly is 0. This is not an asymptotic approach. It truly gets to be 0 right here. I think it was at 8.89. Here's the solution right there. Okay, now let's drain a conical tank.